I'm Dave Hirschberger, W9GR, and today I want to talk about Controlled Envelope Single Sideband, or CESSB, and I'd like to thank QSO today for this opportunity. SSB and Hilbert transforms are a complicated subject, so I'm going to simplify things a little bit and leave out some details. The full details of CESSB are in my QEX article in the November-December 2014 issue. My article is the free sample, which you can download as a PDF. CESSB is an outgrowth of something I did back in the 1970s for controlling overshoot in FM stereo generators. It takes a classic technique for real signals used in FM broadcasting and extends it to complex single sideband signals. In this presentation, I'm going to show you how to almost double the average output power of a typical SSB transmitter without doing conventional audio processing. PEP stays the same. This is not an audio processor, so your signal won't sound more processed. It will just sound louder. Most RF power amplifiers are peak power limited, so if the peaks are big, we have to turn down the amplitude of the entire signal, usually with ALC, so that it stays within the limitation of the power amplifier. Conversely, if we can control the peaks and reduce them, then we can turn up the amplitude of the overall signal, increasing our average power. Here's a quick look at conventional SSB versus CESSB. The audio input signal consists of a tone burst at a reference audio level. The tone burst is followed by accurately peak-limited speech, with the peaks never exceeding the amplitude of the tone. The blue trace is conventional sideband. Notice how the RF peaks exceed the level of the tone. The red trace is CESSB. PEP is the same for both the tone and the speech. Because conventional sideband overshoots badly, we have to reduce the power of ordinary SSB so we don't flat top. In this example, CESSB has more than double the average power of conventional sideband. You might think that if you accurately limited the audio level going into a sideband transmitter, that the output envelope amplitude would also be accurately limited. Well, it's not. And you might think that RF clipping would accurately control the output envelope amplitude of a sideband transmitter. Well, it doesn't. AM and FM transmitter modulation can be accurately controlled by peak limiting the input audio. This is definitely not the case for single sideband. If you put a single tone into a sideband transmitter, you will always get a predictable output amplitude. If you set your audio tone to a level that produces the maximum PEP rating of the RF power amplifier, then you might think that is the correct peak level for speech audio too. Not so. If you accurately limit your audio signal, then apply that well-limited audio signal to a conventional sideband modulator, then it will overshoot like crazy. It all has to do with the Hilbert transform. A Hilbert transform is an audio phase shift of 90 degrees for all audio frequencies. A Hilbert transform happens in every sideband transmitter, regardless of how the sideband is generated. And a Hilbert transform takes nicely peak-limited audio and turns it into a peaky mess with lots of sloppy overshoot. The RF envelope will be all over the place. The Hilbert transform is related to the phasing method of sideband generation. A Hilbert transform is just an audio phase shift of 90 degrees for all frequencies within its range. Some of the earliest sideband transmitters, like the Hallicrafters HT37, use the phasing method. And some of the most modern DSP rigs use the phasing method too. In that method, we take our input audio and apply it to a phase difference network. Over the range of speech frequencies, the two outputs of the phase shift network are shifted 90 degrees from one another. One output was the Hilbert transform of the other output. Then we applied these two phase-shifted audio signals to a pair of mixers driven in RF quadrature, summed them, and we had single sideband. This method directly produced the Hilbert transform. But even in filter-type sideband transmitters, we still get a Hilbert transform even though we don't try to produce one directly. Think about the case where you are receiving a sideband signal with a BFO at the correct frequency. Now, if we shift the BFO phase by 90 degrees, it shifts all the demodulated audio frequencies by 90 degrees too. There's your Hilbert transform. And wherever you have a Hilbert transform, you will have lots of overshoot. About the worst thing you could put into a Hilbert transform would be a square wave. Here's a band-limited 100 Hz square wave being applied to a Hilbert transform. The overshoot from the square wave is almost 200%. Speech clipping before a single sideband modulator will produce huge peaks. The RMS of the two waveforms is the same. The average power of the two waveforms is the same, but the peaks are very different. The square wave is made of a sum of sine waves. The zero crossings are coincident. The Hilbert transform turns the sines into cosines. Now it's the peaks rather than the zero crossings, which are coincident. Here's what the envelope of the resulting single sideband signal looks like with a filtered square wave as its input. Overshoot is almost 200%. Again, putting square waves into a conventional sideband modulator is a bad idea. Let's look more closely at what happens when we take some nice speech waveforms and run them through the Hilbert transform. The blue trace is our input audio. It has come from an audio compressor. The block at the beginning is a tone burst at 100% modulation, that is, the audio level corresponding to maximum PEP of the RF power amplifier. Notice that the blue speech audio does not exceed the level of our 100% tone burst. Now look at the red trace. That is the output of a Hilbert transform filter. All of the audio phases have been shifted 90 degrees from the blue trace. Our nicely peak-limited audio isn't peak-limited anymore. In fact, the overshoot is 59% for this particular speech sample. There's a lot of fuzz on the Hilbert transform output. Notice that the tone burst at the beginning doesn't produce any overshoot. That's because it's just a single frequency. Overshoot happens only when there are multiple frequencies present, where the phase shift causes new points of constructive and destructive interference among the various frequency components. Shifting the phase of a single frequency doesn't cause any overshoot. Shifting the phases of multiple frequencies does. So what happens when we take these two baseband signals and make sideband? It looks like this. We end up with 61% overshoot. That means PEP is 2.59 times what it should be. So we have to turn down our RF output power to avoid overshoot caused mostly by the Hilbert transform. The way sideband envelope overshoot has been dealt with traditionally is with ALC. We don't know what the envelope output level of the sideband modulator is going to be, so we sense RF envelope peaks and we reduce the gain of the transmit path so we don't flat top and splatter. But with traditional ALC, it's too late. The horse has already left the barn. The first overshooting RF envelope peak gets clipped, and that makes splatter. And ALC just turns down the power of the sideband signal you're transmitting. Now you might ask, what about RF clipping? Doesn't RF clipping solve this problem? The short answer is that it helps, but does not solve the problem. Here is how RF clipping is done in conventional analog circuitry. First, we generate sideband in a conventional way. This is the filter method of sideband generation. The filter method will overshoot just as the phasing method does. But what we do is clip the IF signal. Clipping produces IF harmonics, and it produces intermodulation distortion components, which would cause splatter if they were not removed. So we have to run the clipped signal through another bandpass filter. The problem is that the second filter overshoots too. The more you clip, the more overshoot you get from the second filter. Here's what comes out of the RF clipper. The overshoot is now 37% instead of 61%, but PEP is still 188% of what we want, almost double the power. This simulation used a linear phase filter. An analog crystal or mechanical filter would have produced even more overshoot because of group delay variations. Where does the overshoot come from in a conventional RF clipper? First, spectral truncation. Removing the out-of-band clipping distortion components causes overshoot. Second, RF cycle clipping. A conventional RF clipper does not directly clip the envelope. Rather, it clips individual RF cycles. There is a difference. RF cycle clipping in the limit approaches square waves. After bandpass filtering, only the fundamental component remains, but the fundamental component peak of a square wave is bigger than the square wave by 4 over pi. That would be 27% overshoot, or slightly less in practice because we are not producing pure square waves. We can get rid of the 4 over pi problem by clipping the envelope directly instead of clipping the individual RF cycles. But we're going to have to use a different kind of clipper. We will use a divider. This divider clipper is more complicated than a simple diode clipper, but it can be extended to the complex dual path signals we use to generate sideband. First, we apply an input to an absolute value circuit, which can be just a full wave rectifier. The output of that is applied to a function whose output is the greatest of its 2 inputs. You can think of that max function as an analog diode OR gate. That makes the denominator input to our divider. The input signal is the numerator. So if the input signal is between -1 and +1, it gets divided by 1, and there's no change to the signal. But if the input signal goes to 1.5, for example, then the denominator becomes 1.5, and 1.5 divided by 1.5 is 1. The signal is clipped. Now let's extend the divider clipper to complex signals. The input to this circuit would be the alpha and beta signals from our phasing method networks. What we want to limit is the sideband signal's envelope amplitude. The envelope signal is the square root of the sum of the squares of the 2 inputs. This is called the modulus function. Next, we have a max function, which selects either the envelope signal or 1.0, whichever is greater. That becomes our denominator signal, not just for one divider, but for both. When we divide the alpha and beta signals by the same denominator, we only change the length of the resulting vector, but not its phase. After we do the clipping, we have to clean up the spectral mess, and this is done by a filter that rejects the out-of-band components. This method does not clip any RF cycles because there are no RF cycles, so it avoids the 4 over pi overshoot shown earlier, but this thing still overshoots. Here's a graph showing the envelope amplitude of a conventional sideband signal generated from accurately peak-limited audio. As before, the pulse at the beginning is the sideband envelope from a single audio tone. The overshoot is pretty bad, over 59%. Now let's take this signal and run it through the baseband envelope clipper that uses division. The overshoot is reduced a lot by the envelope clipper. We are down to 21.4% overshoot. That's still 47% overshoot measured in power. So what happens if we go through a second baseband envelope clipper? The overshoot is reduced some more, but there's still over 10% overshoot, and that is significant. Let's go through a third envelope clipper. The overshoot is reduced some more, but the rate of reduction is slowing down. We are down to 7.11% overshoot after 3 cascaded envelope clippers. So let's try 4. After 4 clippers, we're down to about 5% overshoot. Let's go to 5 cascaded clippers and see what happens. Now we're down to about 4% overshoot after 5 clippers. Now we're down to 3.4% overshoot after 6 clippers. Convergence is really slowing down. After 7 baseband clippers, we're down to 3% overshoot. Running 7 cascaded clippers gets us close to where we want to be, but at great expense in signal processing. This is definitely not practical in analog circuitry, and it would be pretty expensive in digital signal processing too. But we are getting close to the secret sauce in CESSB. What we need is something that does more than clipping. Since we have control of the denominator, we could create a function that reduces the gain of the divider a little more than what it needs to do for simple clipping. With this modification, we can get the overshoot reduced to a low number in just one pass, and this is the main concept in CESSB. The next step is to modify a conventional envelope clipper. This enhancement allows us to reduce the gain during the overshoots more than a simple clipper would. The gain value in the block diagram is about 2. So if a clipper would divide by 1.2, for example, then this block diagram would divide the signal by 1.4, providing more gain reduction than a simple clipper. That is more than clipping, and this is the secret. If we do this, we can reduce the overshoot to a tiny amount with just one pass through this block, rather than having to go through 7 or more baseband envelope clippers to get the overshoot down. With the overshoot of the baseband clipper solved, here is the complete CESSB block diagram. There are 3 main functions in this block diagram. First, there is a conventional sideband modulator outlined in green. That is followed by a baseband envelope clipper outlined in blue. Finally, there is the modified envelope clipper, which does more than clipping for overshoot control. That function is outlined in red. We assume that accurately peak-limited audio is applied at the input. One thing to notice is that for sideband signals which do not reach full PEP or 100% envelope, the blue and red blocks don't do anything at all. CESSB leaves low-level signals untouched. It only does something to the signal when there is overshoot in the sideband modulator. Another thing to point out is that the last function in the block diagram is a baseband low-pass filter. This corresponds to a bandpass filter at the IF. This final filter ensures that the bandwidth of CESSB is sharply limited, and we will see that the amplitude is also accurately controlled. The next few slides show the result of the CESSB system. First, here is the envelope coming out of the first block, the conventional sideband modulator. Overshoot is 59%. That would be 253% of the reference tone power. After the baseband envelope clipper, we are now down to 21% overshoot. And here is the final CESSB output. Now that's what I'm talking about. Overshoot is just 1.6%. The bandwidth is limited and clean as a result of the final bandpass filter, and the amplitude is accurately limited too. This is just what we want, to be loud and clean without splatter. So, what does all this mean? First, with CESSB, your transmitter will put out almost twice as much average power as before. PEP will remain the same, but average power will go up. It is nonlinear, but artifacts are generally inaudible. CESSB makes ALC unnecessary. Just set the CESSB modulator to drive the RF power amplifier to its full PEP capability. ALC usually won't hurt anything if it is enabled, and it can help set the drive level into a linear amplifier. RF power amplifiers won't be thermally strained because at maximum PEP, the RF amplifier is operating at maximum efficiency. If average RF drive is reduced, as it would be with conventional sideband, the dissipation in the RF amplifier actually goes up. Power supplies will be strained. As average RF output power goes up, so does power supply current. Make sure your power supply is up to the task. CESSB will have systems implications. Current sideband technology doesn't do very much baseband audio processing because conventional sideband overshoots like crazy. So today's sideband radios rely on ALC and sometimes RF clipping. As we have shown, these techniques really are not very effective. But with CESSB, the audio processing can be and should be moved backwards into the baseband audio domain. Modern broadcast-type multiband limiting and distortion-canceled smart clipping can be applied with much better results than a simple wideband RF clipper. So I think we will see the development of some very good speech processing algorithms which can be combined with CESSB for no overshoot. Bottom line, your sideband signal will be louder without sounding more processed. Plus 3 dB is only half an S unit, but if you're down at the noise level, 3 dB can easily make the difference between copy and no copy. And this 3 dB comes a lot easier than doubling the size of your linear or stacking 2 beams instead of just one. Where can we get it? FlexRadio has had it since summer 2014, and it was added to the OpenHP SDR library back in January 2015. Remember, it is more blessed to transmit than it is to receive. Thank you for your attention. My publications on CESSB are November-December 2014 QEX, January-February 2016 QEX, and February 2016 QST.